Well, friends, today we're looking at section 6.1, the graphic of antiderivatives, and we're going to do a problem from the winter 2014 final exam, and this is problem number 5. And the problem gives us a graph that is h of x shown below, and they note that a portion of this graph between 4 and 5 is part of a circle of radius 1, centered at the point 50, that h of x, capital H, is a continuous antiderivative of little h with h of 0 equals 2. And this is very important because this tells us that really we can have an infinite number of antiderivatives, and the specific one that we want has a seed value of 0 at 2. So I can just come right here and I can plot that right there, that 0, we hit 2, but I'm going to use that and the areas here to fill out the table. So what we can say is in going from 0 to 1, the area there is 1. And so in going from 0 to 1 on my parent function, the function increased by 1 unit from 2 to 3. Let's go again. In going from 1 to 2, the area here is 2, and I'm just counting squares. And because this is a negative, that means our value decreased from 3 to 1. Let's go again. From 2 to 3, the area here was once again 2, but because that area is below the x-axis, we went down 2 units and we hit -1. And then similarly, from 3 to 4, well, that's only going to be half a unit, or it's only going to be 1 unit, because that's half of the square or rectangle that contains 2. And so we went down 1 more unit, and we are at -2. 1 unit from where we were at -3, or where we were at 3. Finally, from 4 to 5, we increase by how much? Well, it's going to be pi r squared, the area of a circle, so pi 1 squared, but I only need 1/4 of that, and so we went up by pi over 4. So our exact value here is going to be -2 plus pi over 4. Okay. Now, what I want to do is I want to actually graph this half together, and then we'll start thinking about what happens when we go back in time. So I certainly can plot the point 1, 3. I certainly can plot the point 2, 1, 3, -1, 4, -2. And then I should think about pi is around 3-ish, so I divide that by 4. I'm going to get around 0.75, so -2 plus 3/4 is going to be around -1 1/4, so we'll be around right there. Okay. So now that we have this, we can begin to think about how the slopes are, because here the slope is a constant 1. And that's going to correspond to the slope of the parent function, which is right here. So our slope was 1. This is a graph of the slopes. The slope is 1, and I have a line with a slope of 1, and we're happy. Look what happens from 1 to 3. We also have this slope of -2 the entire time, and we have a linear function. Make sure that it looks very linear. Mine doesn't look as linear as it could right there, but that's fine. Now, from 3 to 4, something changes, right? We start out with a slope of -2, but we finish up with a slope of 0. And so what I like to do is I like to dash that slope in, yeah? Now, this is linear. And the antiderivative of a linear function is a quadratic function, right? I mean, if I have a quadratic, I take the derivative, we get the linear function return. And so the antiderivative is going to be quadratic here. The slope starts out at -2, and winds up at 0. And I'm just going to make that quadratic function right there. It doesn't have to be perfect. What we do have to say is that because this function is increasing, it means that our antiderivative is going to be concave up. Let's go again. Now, the slope starts out at -4, or sorry, at 4, the slope is 0, and we dash that in. And at 5, the slope is 1. And I just kind of dash in what it looks like to have a slope of 1. And now we are an increasing function, and so once again, we're going to be concave up here to get our antiderivative, and we're done, at least with this half. Now, going backwards, I could certainly do any of these problems with the fundamental theorem, but I prefer to think of these things just as displacements. And so the area here, once again, is 1. And so from -1 to 0, my function increased by 1 unit. So instead of being at 2, we had to increase by 1 unit to get to 2, and so we're going to be at 1. Let's do that again. This area right here is 1 as well, but it corresponds to a decrease of 1 unit. And so my function from -2 to 1, it decreased by 1 unit. We wound up at 1, and so we have to be at 2. Let's try again now. Right here, from -3 to -2, the area is 1. And so my function increased from -3 to 2 by 1 unit. And so we're going to be at 1. The area is positive. It increased. I was at 2, and so we had to be 1 lower to deal with that increase. And now I can think about this in 2 steps or 1. Let's go with 2. So this has an area of 1.5. And so my parent function did what? It increased by 1.5 units and wound up at 1. And, if I wanted to do the fundamental theorem here, I could. I could say that the integral from -4 to -3 of little h of x is, I guess I have dx, is equal to what? H of -4 minus h of -3. And some people do this every single time. I'm not that in love with it. The integral represents the area, and so that would be 1.5. We don't know what h of -4 is. I'm sorry, my endpoints here are in the wrong order. It's got to be h of -3 minus h of -4. We know what h of -3 is. That was 1. We don't know what h of -4 is. And we know that that's equal to 1.5. And so I could bring the h of 4 over, I could bring that 1.5 back, and we got exactly what we thought, that we would have a -0.5. As much as I love the fundamental theorem and playing with it, I think it takes too much time. And I think we're better off, like I said, saying that we're growing by 1.5 units. We're at 1, and so we had to be 1.5 units lower previously, and so we're at -0.5. Let's go again. Here we have 0.5. And so in going from -5 to -4, we grew by 0.5 unit. And we wound up at -0.5. And so that means we're going to have to be 0.5 unit lower, and we'll be at -1. Let's plot these points, friends. There's our -1. Here's -0.5. At -3, we had a +1. At -2, we had a +2. And at -1, we had 1. Okay, so now that we have our points on our graph, we can begin to break this thing down into a series. And so right here, we have a linear function because we have a constant derivative. And so the slope is still going to be 1. Slope is 1 from -1 to 1, and the derivative is a constant. Now, from -1 to 3, I have a linear function. And keep in mind that a linear function means that the antiderivative is a quadratic. Now, I am going to dash a few things in. And I know that at -1 on this side, the slope is going to be -2. So -2 slope looks like this, right? And I'm just kind of dashing it in there to say, hey, look, it's going to start out with that negative. At -2, the slope is 0. And I'm just going to dash that in. And at -3, the slope is 2. And I can just kind of envision what that's going to look like. Linear derivative quadratic antiderivative, and I can sketch that thing out and be happy. I want you to notice that on this side it's steeper than it is on the other. Let's finish up now. And the finishing move here is to recognize that, hey, this is a linear function, which means that the antiderivative is going to be quadratic. Now, the slope at -3 starts out as -2, exactly like we have there. The slope at -5 is 0. I can dash that in. And we're going to have a quadratic function because this is linear here, and the antiderivative is going to be quadratic. And we're out.